some basic information about like the types of batteries that we actually see in the real world. Kind of like I said, those nickel metal hydrides. Something like that is far more common than, like a beaker with some copper and a beaker with some zinc. Okay. So I want to talk about a few popular types of batteries you may have heard of. One, of course, being the lithium ion battery, such as in your cell phone or your laptop, in electric vehicles. And not all of these lithium ion batteries operate this way. And again, a lot of that is because it's proprietary. We're not allowed to know from the manufacturers how they work. But this is a pretty typical methodology for how this works. Okay. So we have this crazy looking reaction here, Li1 minus X, where X equals 1 in a fully charged battery, and X equals 0 in a fully discharged battery. So for example, if X equals 0 right here, then we can see I've got lithium over on my cobalt oxide, which is my anode, or the cathode, okay? So when the battery is fully discharged, so when it's dead, so you can see discharge, we get these lithium ions that can sandwich themselves in between these cobalt oxide structures, okay? So of course, this is all tightly packed, much like that little tiny battery, right? There's no beakers filled with liquid, okay? But now when X equals 1, so you can see 1 minus 1 is 0. Now that means the lithium has completely migrated over to the anode. And of course, it involves use of graphite because graphite is a wonder material. And what's kind of cool, it's hard to see this, but here is our graphite ring, and the lithium ion gets sandwiched kind of right in between those rings, which is pretty cool, okay? So once again, when it's fully charged, we don't have any lithium at the cathode. And when it is charged, lithium migrates over to the anode. And because of the way this lithium ion is migrating back and forth, that will induce a flow of electrons. Either depending on if you're in the charging mode, the electrons will flow in one direction, and if you're in the discharging mode, the electrons will flow in the other direction. Okay, and so again, what's really cool about these things is you can make them so small and compact. And at one point in time, there was plenty of lithium, but now we're actually kind of starting to run out of lithium. So we're having to kind of figure out how to adjust this as you see more and more electric vehicles come online, or as we are shifting away from fossil fuels. That's going to be another thing that we have to consider, right? Mining all of this lithium is not without environmental consequences, okay? So this isn't perfectly environmentally friendly because we do have to dig up all this stuff from the earth. All the same, there's no carbon footprint once you've got that lithium battery in there and you use it for a long time. So that's one way to combat the environmental problems with mining lithium is use this thing until you can't use it anymore and dispose of it properly, right? There's a lot of channels where you can turn in your old electronics, and a lot of companies are getting much better now at reclaiming these materials to be more environmentally friendly. So use that cell phone until it's falling apart. Use your electronics until they can't be used anymore, and then dispose of them properly. That's the way to be the most environmentally friendly with all of this new battery technology. Okay, so an older battery, but still very common, the lead acid battery. So this is your car battery for the standard, of course, internal combustion engine, right? This is the thing that makes your engine start up, okay? So it's a rather complicated reaction, but it's lead acid. So of course that means it's got lead and it's got acid. It's got sulfuric acid and it's got lead. And so that's why these things can actually be quite harsh for the environment if you were to just chuck it into a river or stream. And also they can be quite nasty to you, to your body, right? They can get corrosive. So if you've ever worked on a car battery, you probably know that already, okay? So the cathode material gives you 1.685 volts. The anode is negative 0.356 volts. And right, E cathode minus E anode, that becomes a negative negative. So you get 2.041 volts. There's 6 of these things in series. So when you say times 6, that's where you get roughly your 12 volts. Okay, and so again, maybe you car heads knew that you get 12 volts out of your battery, and that's why, because you've got 6 of these cells in series operating at roughly 2.041 volt per cell. Okay, so let's take another look at this in more detail. So these are very cool, and so they can operate in charge mode or discharge mode, which is what your alternator does. So let's talk about that. So when you are using your battery to start up your engine, okay, so load the starter motor, right? So we get this reaction to go. So electrons proceed from anode to cathode, right? Here's the battery top view, the negative end to the positive end. And this discharge will fire up this starter motor, okay? And that actually will deplete your entire battery quite quickly. So if any of you have had issues with car batteries dying, it's because typically in one start, it discharges the battery almost completely, okay? But now once your engine starts up, your alternator takes over. So this is your alternator, and it's getting power from the engine, and that can induce the reverse reaction now. And so we still have electrons flowing from anode to cathode, but you also have some other very smart pieces of equipment in there that can switch those two things over. And now your alternator will drive the electrons back to the other side, just while your car is sitting there running under idle, right? It charges the battery right back up, okay? And so if you've ever had problems with that, likely it's your alternator. There's all kinds of car hacks out there, right? Your alternator stopped working, hit it with a hammer. All this fun, goofy stuff. And there actually is some validity to some of those things, right? You just need to get this to spin so that it'll start charging your battery back up. And so this gives you an idea of how much you can actually discharge these things. And this is what I was talking about, how in reality, we really only use like 25% of our battery or so, okay? Because when you see that, that's a really sharp fall off. So when we look at this level, or excuse me, not 25%, I knew I was backwards on that, roughly 75%. So I'm gonna draw a line, around the 75, 80, let's just call it 80, okay? So we're starting at about that 2 volts or so, 2.04 volts, right, for one of those things. And as you can see, as it discharges, this falls off. And then when you hit, right around 80%, I knew I was getting that number wrong before. When you hit right around 80%, it really falls off, okay? So this is why we actually only, we only need to, we can only discharge about 80% of our battery or so. Totally backwards on the last video. I'm not fixing it. So where I was saying like 25%, I was really meaning like 75%. And based on this figure, it's really like 80% in any event. You don't use 100% of your battery, okay? Because this cell potential really falls off as material is pushed over from cathode to anode and vice versa. And the last type of cell that I'll talk about, which was gaining a lot of promise about 15 years ago and less so now, and that's the hydrogen fuel cell. And the way the hydrogen fuel cell works, the fuel that it uses is just hydrogen gas at the anode, okay? And so there's more complicated materials going on here, but effectively you have hydrogen at the anode that you have to supply. So typically like you'd have a tank of hydrogen. Oxygen is typically grabbed from the air in these types of fuel cells. And so you have hydrogen and oxygen meeting from anode to cathode, and the product is water. So it's kind of like an almost ideal situation, right? You imagine like the only fuel you need is hydrogen and the only byproduct is water. And so this was gaining a lot of promise as a replacement for the internal combustion engine, right? Replacement for fossil fuels. However, almost all hydrogen on Earth comes from fossil fuels. So there's a little bit of irony there. So H2 does not exist readily on planet Earth. It's such a light molecule that it can actually escape out the atmosphere. So most H2 that we have available, we've created, and we've created it from fossil fuels, from hydrocarbon. So we call this petroleum cracking. So we release the hydrogen in that hydrocarbon to make H2. And it's not really all that different than the lithium story, right? We have to mine lithium out of the earth, and that is also not very environmentally friendly. So it's hard to weigh, all of these things, which is going to be ultimately the best. And another complication of the hydrogen fuel cell is you imagine now having a hydrogen fuel station, right? I wanted to say gas station, but it's not a gas station. It'd be a hydrogen station. Well, hydrogen wants to be a gas at room temperature. And so to deliver hydrogen to a hydrogen station, you have to compress it into a liquid. And so you'd have all these big like tanker trucks driving around filled with H2 liquid. That would be disastrous if one of those things got into an accident. It's already bad news when we have liquefied methane tanker trucks driving around. Hydrogen would be a nightmare scenario to see one of those things explode. And furthermore, it takes an enormous amount of energy to condense hydrogen into a liquid so that you can transport it. So I think that's why really the electric vehicle revolution has taken off in comparison to the hydrogen fuel cell. And as you imagine, right, if you can combine these technologies with green sources, then that's even better. So you can make hydrogen in other ways besides fossil fuels. So you could make hydrogen from actually the reverse process. You could make hydrogen starting with liquid water, but you would have to use energy to get that to split up into H2 and O2. So there's a bit of irony there, right? You have to use energy to make energy. Such is life. Okay. So, but if you did that with solar power, right? If you did what, making hydrolysis of water, or I should say electrolysis is what this is called, then this can actually be quite environmentally friendly. You still have the downside of having to compress that H2 into a liquid, very complicated to transport that stuff around, which is why, once again, I think the electric motor has really taken off. And ultimately, if you can charge your electric vehicle with solar panels, right, not from the grid, but maybe your own solar panels, that's like even better. Okay. And of course, we could talk about how solar panels work. They work just the same way as all this stuff we're talking about. But then I'd be like doing an entire course on this stuff. So I hope I intrigued your interest with electrochemistry. We did go through it kind of fast. But to me, this is like where we need to go as a society, is really getting rid of our dependence on fossil fuels and taking advantage of these battery technologies, and also exploring how we can make these batteries in a more environmentally friendly way. Okay, folks, thanks for listening.